Okay, hello everybody. Good morning. So we are getting close to end of this semester. Today formally we have our last lesson. So also today's course is not hard to understand. I think should not be big deal. You can easily get the point. But before starting the course, do you have any question? Is everything clear so far? Good. So after course, I will have a quick explanation about the project and the exam and the process that you will go through. You already know, but I will have a brief explanation. But anyway, let's first discuss about today's course. So today we are going to talk about decision trees and random forest algorithm. The concept is quite easy to understand. If I remote works. I think go to John, please, and take another remote. We have it there. Yeah, it worked, but better to wait for student come back. Hardly, but better to have it back up now. Okay, thank you. Okay, so we are talking about decision trees. Sorry for the interrupt, it didn't work. So we are talking about decision tree and random forest in this chapter. So what we will see, we will answer first of all what is the decision tree algorithm. Then we will talk about different splitting measures for the decision tree. We will see, okay, if you want to make a decision tree, it's kind of tree that helps us to make decisions. But we trying to split the data. When we trying to split the data into, for example, two parts, we should see that how we can have different splitting measures over there. Then for that splitting also, we need to answer how to find the threshold and which one of the features based on the data that we have, we should do that thresholding. We will answer each one of these. Then later we talk about the advantage and disadvantage of the decision tree. We will see a practical example, the example that the data set that I gave you during the class. We will solve it, we will see how that works. Then we talk about the understanding random forest algorithm. That random forest algorithm is based on the decision tree structure that you will see which is easy to understand. And generally, after finishing today's course, you should supposed to know decision tree and random forest algorithms both together for either regression and classifications tasks, because both of them are able to solve those problems. So let's dive in step by step. First of all, what is the decision tree? Decision tree is popular supervised machine learning algorithm that both can be worked for classification and regression. So it is popular and it can be used over there for regression and classification. It is widely used. Why? Because it is simple, it is easy to interpret. It means that we can discuss it what is happening easily, and also they working with nonlinear problems. We are not limited for only linear problems that we needed to predict a line over there. So decision trees, there are different elements in decision tree. One of the most important elements is branch. We have different branch in decision tree. That branch representing decision rules for us. After branch, we have decision internal node, so that decision internal node actually represent us the feature, and based on that feature, we can make thresholds to split the data. And after second element, we have third element, the most important element, that is the leaf node, and leaf node represents the outcome. So how visually it looks like, to make it easier to understand, we can have a look at here. We have decision node over here, and different decision nodes. We created three. These are leaf nodes, and this is whole branch. So we will discuss what can be inside decision node, but basically for decision node, we can say we have some features inside that we want to find some thresholds in order to split our data into different groups. You may at the beginning think, okay, this looks like splitting the data to the left and right, for example, into two. But how we can solve regression problem with this looks like classification. We will see how the differences is and how that works. So if you want to have another definition, we can say it looks like flowchart, but it can work for very complex and big data. We need to just determine the features that we have, and based on those features, we can apply decision tree in order to even solve nonlinear problems. Another view, we can say the branch represents the outcome of the test of the data that we will inject to our tree. On the other hand, the decision node tests a feature attribute. And finally, leaf node represents the class label if we have classification, or numeric value if we have regression. So it means that we want to construct a tree, Then the leaf nodes represent us the class of data that we have, or in regression task, the values that we want. So the general idea should be clear. We want to have a tree, some data comes, and we want the leaf nodes to have as classification task or regression task over there. So again, we can have a look at the figure that everything should be clear, the same tree that we've had. So of course, we should have some concept based on the decision tree learning. Kind of the learning procedure in machine learning technique should be involved in order to find the answers that we want. We say we want to construct decision tree using a greedy top-down approach that we call it recursive partitioning. So that means that, in different techniques of the machine learning or different algorithms, we can have the problem and break it down. But here, what we say, okay, at the beginning we don't have tree, and we want to, from top-down approach, split the tree, split the tree, split the tree. Actually, we want to split the data from top-down view. Not we have a tree, for example, then we want to cut it, make it small. We can say every leaf is, for example, a class, a value that we per value a class, then we cut it. No, it is top-down procedure. So single tree can include different features, not only one feature, and we can place it in different internal nodes. It means that, for example, you have a problem with including height, weight, age, with, for example, these three features. It means that if you know in regression tasks what we were doing, we were like including all of these three together. In decision tree, when you have a leaf node, not leaf node, when you have an internal node, so we can choose one of the features to include there as a splitting metric for us to split the data. And this says that we are not limited to only one metric in whole tree. For example, we want to do the classification task and construct a decision tree based on only age, based on only weight. No. At each leaf, we can switch these, and we will discuss how we can choose each one of these metrics, these features over there. There is one small point. We already have seen and discussed the feature selection. We can already have the feature selection based on our problem. Like our problem has 100 features. But from those 100 features, we only need 4. Feature selection already run. Then based on all those 3 or 4 features that our data has, then we can apply this technique over there that we will see. So what we do, we perform recursive partitioning until some stopping criteria comes. So we want to create the tree, and at some time stop, and the stopping point is reaching a maximum depth or reaching a minimum number of samples at each leaf. It means that when you are like, you have 100 data, you try to split them to 50-50, for example, then split this 50 to 20-10, 30 or 40-10, for example, then the numbers are getting smaller, number of samples that you split into each one of the leaves. So we can say, okay, if minimum number of samples reach over there in the tree, we can stop it. This second one means that. But here is maximum depth of tree. That is, I think, quite clear for everybody. So what are the different splitting measures? In order to do the splitting, we need to have a measure. These measures, we already have seen few of them. For example, for regression task is simple. For regression task, the measures that we can use, for example, is mean squared error. Another measure can be mean absolute error, MAE. So I think I didn't introduce this, or I didn't mention this. It's exactly the same, just you don't have a square. It's like absolute error, MAE. also is popular to see. So for regression tasks, we are going to use one of these. I will also show you in the implementation an example. On the other hand, what if we have classification tasks? For classification tasks, we need to discuss some more popular, more important metrics. There are two over here. One is Gini impurity. Gini impurity is very easy to understand because it measures the probability of misclassification. We want to say how many of these data. So we want to have like 100 data, split it to, for example, some part to the left, some part to the right. In right part, we want to say how many of they are misclassified, and Gini measure can do that for us. How it looks like this. Gini impurity is equal to 1 minus sigma of the probabilities, square of the probabilities. So this sigma is summation over all classes, and this pi, the probability of the belonging to class I. So if the data, the sample data from data set that we have, we choose one data from there, and we run Gini impurity, and we find the probability of the, is it belong to that class or not. For example, I can write, like let's say 70%, you have class of yes or no, just two class, yes or no. Let's say it's 70% and 30%. Then what we do, we write one minus sum of the probability of the i's, 0.7 added by 0.3 squared. Then what happens? You get some probabilities, for example, 0.4. And this 0.4 says that 40% probability of misclassifying that data over there. That if you sample, the data sample that you chosen is 70-30, 40% is misclassified, the probability of misclassification. This is a Gini impurity that we can run all our data set and data. And I will show you also how it works. That's also with libraries already built in implemented, not big deal. On the other hand, we have another metric is entropy that we already mentioned it, but here entropy measures the level of uncertainty. This is level of misclassification, this is level of uncertainty. And how it is, the equation is very simple. Entropy is equal to the negative of the sum of probabilities times log 2 of the probabilities. Same probability, that can be the probability over there. And just this equation gives us how much certain we are based on the classification. Again, we have data. We want to choose a feature based on the node, then split it into two based on one threshold. I will show you visually quickly. Then when we split it, we want to say, okay, what is the splitting measure? We can apply, for example, Gini impurity if you have classification task. Then run this simple code on the data over there. You will have some values like there that shows for you. So now let's put all together as a form of algorithm and see step by step what is happening. For decision tree algorithm, first of all, we have the splitting measure. So we need to choose the splitting measure that we introduced in previous slide. What does it say? It says that, okay, we select the splitting measure like MSE, Gini impurity, entropy, or whatever we want, the technique that we want. After that, we need to determine best split for each feature. So this is very important here. For each feature, we need to determine the best split. You have a data set. Again, you have height, weight, age. Each one of these are features. For each one of the features, you need to determine the best split point, that how to split it. Then we will measure it, then we choose which feature is good for that leaf. How this is happening, let me show the procedure. Determine the best split for each feature, evaluate the possible threshold for that feature. Possible threshold means that, so for example, age. For age, my data is like 1 year old to, for example, 85 years old, right? Now I want to find a threshold. This is my data, I want to say how, based on age, let me write it here. So where can be the splitting point? Where is good to split it? And how can I find this? I will discuss it, but the measure that I have also shows where the point is to split it into two with decision tree. So we want to evaluate the possible thresholds. Threshold means this, where the value should be. Threshold is the definition that in machine learning we discuss it. So for each feature, we consider a range of potential thresholds that can be done, and we find the best one. That in next slides I will have discussion how it is. After, let's say we know how to find it, then after finding the best threshold, let's say we try all of it. You can now consider you try all of the possibilities of thresholds, then say for which one the value is the best. After that, we calculate the impurity or information gain for each splitting measure for this one. After the calculations that is happening after the splitting data based on the impurity gain, for example, for each that we calculate, finally we find the best threshold. That finding the best threshold can be, for example, maximization of the gain that we have, maximum of this or minimum of this value that we have, depending on the measure that we are choosing. For example, if it's uncertainty, we need to decrease it. So these three steps helps me to determine the best split for each feature. For each feature, I run it, then see. For example, for feature 1, the best threshold value that I can find gives me a value V1. For second threshold, for second feature, I have another value. For the third one, I have another value. Then which one is the best? I choose that feature as best value, and for the tree, for that specific node, I split it based on that. That is the same explanation that I explained to you. As third step, after first and second step, we split the data. After you find those best feature and best threshold, then we split the data, and when you do the splitting the data, we determining the best threshold and splitting the data into the two groups. That is clear, I explained it already. And as fourth step, we recursively doing the partitioning. We do the repeat these steps until stopping criteria arrives. So 3, data comes, we split based on finding best feature and best threshold, and per each one the gain is split. Per each one the gain is split, and we construct the tree until we reach stopping the criteria. That this can include, as I mentioned already, reaching a maximum depth or minimum number of samples per each leaf over there. After you do those steps, you need to, if you have classification problem, then for the leaves that you have in your tree, as I mentioned, is indicating your class or your regression values, so that we assign class labels if you need it. That we say, okay, this is class yes, no. This is class true, false. This is class, you have 10 different types of items. low, high, medium, extreme, you assign the labels over there. So we will see examples soon, visually how this is working. But there are some critical points before getting to that point. First of all, the question is how to find thresholds and best features. As I mentioned here, we need to find a threshold to split data, right? How we can find this? And after finding threshold, we can evaluate for each feature, for each x's, and to see which one is better. How we can do that? If you think a little bit in depth, you will see that, oh, this is not easy problem also over there. It's already optimization problem. It is NP-complete problem. When I'm talking about NP-complete problem, I mean that if your problem state space is too big, exponential, then you cannot solve it with like for loops usually. You cannot search all possibilities. It takes forever. If you use all existing computers in the world, all servers, everything, and if you want to solve this one simple problem, then it takes like millions of years with all computational available processing units that we have. So those are NP-complete problems, are famous techniques, series of study. But what we do here is, of course, we prefer don't do that. If you want to solve this complex problem already, we get in trouble, because we want to solve another problem, then here we should find the threshold, and that's problematic. There are different techniques to do this. So this is the same explanation that I told you. This can be minimizing impurity or maximizing problem depending on what we have. This is NP hard problem. And what we do instead, we use various strategies. That one is greedy approach. So to find the threshold, there are some techniques for decision tree that called greedy approach, and they are only wanting finding locally optimal decision thresholds, not the best possible one. If you say, okay, I only want to find the local one, and still it works very fine, so that then you can use greedy approach, that you don't need to consider global optimal value. Another technique is heuristics. Heuristic is popular in artificial intelligence. I teach, for example, in the course of artificial intelligence. Just to simply knowing, consider a subset of values that use a kind of evaluation metric in order to help your algorithm to go and solve the problem. For example, if I want to solve the path planning problem from this point to that target point in the corner, with heuristic, I can measure direct distance and say, this is my heuristic that I want to, the best distance that I can have is from here to there. And based on that, write a heuristic in order to solve my problem. I don't want to open this in details because it takes a long time. If you are interested in, you should study it. If you don't know, if you pass artificial intelligence, you already know. So greedy approach, heuristic. And on the other hand, also you may say, okay, no, I want to find the best optimal threshold there. Then you can use optimization techniques. Popular optimization techniques for decision tree, for example, is grid search. Is a technique that you can find proper values for splitting over there. Any question so far? So that was one point that we needed to understand. Second point, how to handle continuous features. You may think, okay, we know the discrete and continuous environments. Actually, with decision tree, we are discretizing. We are splitting the data to discrete number of points. How much we do that still is most likely discrete, right? And how this is happening with continuous features. We say there are some strategies for handling continuous features on decision tree. Two of them are very popular, but the concepts are very close and hard to even distinguish. One is binary split. With binary split, we create binary decision rules by comparing feature values to a threshold. For example, we can say the age is smaller than, for example, 10. The threshold that I determined there as 10 is a threshold that I can say age is smaller than 10. For binary splits, usually these thresholds manually and already determined. I already give it here. On the other hand, this is called binary split. On the other hand, threshold-based splits is a technique that we explained. They are determining the best threshold split, and they are working by determining optimal threshold by evaluating different threshold values that in previous slide we discussed. That what we are interested in, mostly the threshold split, and most of the things that we solve and use is based on the second one. Both finally doing the same thing, comparing the features with threshold, but now we can handle continuous features. So let's now clarify everything with seeing one example. So in the example, let's consider we have regression problem. In the regression problem, what we had in the class, you solved many times advertising example. I'm going to show if we apply decision tree on that problem, exact same data set that you have. What will happen? If you run that algorithm, we will have a tree. I just in this slide present first root node and the two of the splits. You can see some elements inside. What are these? Let me introduce. So x of 0 is smaller or equal to some value. So what is this? This is the feature. Which one of the features that I have? Let me see if I put it there. Yes. So x0 was social media, x1 was TV, x2 was billboard. So it says that in this node, my chosen feature based on the evaluation, best feature is the social media. And my splitting threshold is 243.75. If you do that, the square error, the MSE, mean square error, is 27. Here in this node, we have 20 samples. Our data set has 20 samples. And the value that we can have in this node is 20 point something, 445. What does it mean? It means that for these values, for these features that I had some prediction, right? The selling amount. So the value represents the average of those in this node. So average of these 20 values output is 20.445. And the chosen feature to split is x0, social media, and the value 243. And if you apply this chosen split, what happens? We have data who are smaller than this value, who are bigger than this value. The bigger ones go to the right, smaller ones go to the left. If we look at the right node, number of samples is 9 here. 9. And if you look at this left side, number of samples is 11. It says that among these 20 values, based on social media values, right side and left side per data set, the data that I have. So what is the value representing, what representing the value? The value represents the output of average of all these nine data that I have here. And in this side, the value represents the average output prediction values of the these 11 samples. Now, I want to continue the same procedure Here for this node, I want to find best feature and best threshold. Best feature here, the algorithm has been found x1 for me, TV, and threshold value is this. On the right side, here, the best feature to splitting for this data, for 11 data over here, x0, and the threshold value has been found 142. How? Based on, for example, Gini impurity, MSE, because we have regression problem here, it is mean square error. And this is the minimum value based on, this is minimum squared error. This value is represented the minimum one based on all possible thresholds and all those three features that can be found. The technique has been searched inside and found this value for me. And here the technique does the same and found for me. Any question? Is this clear? If you understand this, you understand whole decision tree problem. With this slide, everything should be clear. Again, everybody listen. We have 20 data. The data set that you have in the codes, the data for social media, TV, billboard. These were X features, amount of advertisement here, and we had some value over there as prediction. Those 20 data, now I split it based on x0 to the left and right. 9 go there, 11 come here. And the value for 9, the prediction value for 9 is this value average. And here is this value 16.70. Now I want to again split this and again split that. And if I continue that, before that, how we can implement it in Python, you can see in 3 lines, scikit-learn that tree, import decision tree. Then we have the regressor, because we have regression here problem, decision tree regressor from library, decision tree regressor implemented, and regressor.fit x as input, y of the regression as output. You give the input and output, or x and y, then you will have this tree over here. I will show you all together also. So if I run whole that, you will have this tree. This is the result for the data set that you have. 20 data for advertisement. And for those 20 data for advertisement, you can see that here is split it by x0. x0 as social media, to the left, right, as we explained. If you come here again, here is split it by x0. Threshold is something else. Number of samples is 4 here, number of samples is 7 here. Again, this 4 is split to left, right. Number of samples is 1 here, that becomes leaf node. Then right side, number of samples are 3. Then again, these 3 is split 2, 1. These 2 is split to 1, 1. So all the leaf nodes here are included as 1, 1, 1, 1. So only we have 1 sample per each leaf node. And what does it mean? It means that now, if I give new data for this decision tree, for example, let me say, I don't know even what's the data set. Here. Based on the decision tree algorithm that we studied, after constructing this tree, let's say I have a sample data. For example, I say x0 equal to 12. I write something random, I don't know, 45. x2 equal to 62. So it means that I have a sample data. I say I advertise on social media for 12 minutes. TV 45 minutes, billboard 62. Then what decision tree tells me? What should I do? I come to first node. x0 is smaller than this, is smaller equal to this or not? 12. It is smaller, right? If it is smaller, I come to here. Then based on x0, again, if it is smaller, come here. Again, it's smaller, come here, finished. If it was bigger, for example, if we put some some bigger value, 312, then it goes to here. Then instead of x0 this time we check x1. What is the value? It's smaller, come here. And continue to finally reach a leaf. And when you reach a leaf, the value that you have is the prediction. For this amount, the prediction value is, for example, 19.9. Or, for example, is like 20.2. Clear? You see, very simple and easy to move forward. Now, what if for the same problem I want to solve classification? What I did, same data set, I add some labels. I said, okay, let's have same data set and let's make it as classification problem with adding some labels. And what I did, I said, okay, medium, low, high. The effect, I can consider classification problem, amount of advertisement that you're doing just by 3 words. Low effect, medium effect, high effect. Then it becomes classification problem. I did the same thing. And when you do the same thing, this time again x0 for example is smaller than some value, but the metric should change. Metric is Gini here. So instead of mean square error Gini, we studied how to calculate. At the beginning again I have 20 number of samples, and here we have value equal to 1010. That here this value shows the frequency of the number of values per each class that we have. Then split into the left, right, to the left, right, to the left, right, to the left, right. Finally, you see that on the leaf nodes, for example, this is medium. The class is medium if you come here. The class is here low. The class is here medium, low, medium. Actually, I think I considered 2 classes here, low and medium. Yeah, 2 classes only. That's why we have in values 2. I didn't consider for simplicity high, just 2 classes, low and medium. Can you do more? Can you do 3? Yeah, of course you can do 3. Consider 3 classes, then this will be 0. For example, instead of 10, will be distribution. For example, how much you have, then the classes will be split. How you can implement it? If you want to use libraries, again, very simple. From scikit, you can do the decision tree classifier and finally fit it 3 lines. But of course, we prefer to implement ourselves as machine learning course and construct the tree ourselves. So any question up to here? Is it clear, crystalline? We had data, we considered classification task, regression task, and constructed tree, and we saw how we can solve it. Now again, if new data comes, I give new data, it can give me it is in class of low or it is class of medium here. Okay. We have a couple of more points. One is pruning. Of course, we may have overfitting problem here again. Our tree maybe overfit the data and gives exact values, exact tree for the data set that I have, but for new data works bad. Same problem can happen here. So what we can do pruning, and different pruning stages can be pre-pruning or post-pruning. Pre-pruning, it means that stop growing the tree early. Don't let the tree grow and completely understand whole data. Stop it in some point. How we can do that? Bias variance trade-off. The same technique of regression, we can use it over here. Or we can consider some conditions like maximum depth. If the depth is this, don't go anymore. Maximum samples per leaf, Don't go up to one sample per leaf, because that's overfit, of course. Learns every sample exactly. Go like maybe 10 sample, 5 sample. Based on data set size, don't let to grow the trees for each one of the samples. Or some minimum improvement of the tree based on the Gini or MSE, just stop it based on that. That is pre-pruning. Post-pruning says, okay, construct whole tree completely, then cut some of them. Prune some of them so that you don't let your algorithm to be overfit. Similar to what we were doing in deep learning and neural network with removing some nodes from the neural network nodes there. What are the key advantages of the decision tree? First of all, easy to understand. Easily you see that you can understand. You don't need to even be very expert in this field. They are able to capture very complex relationship in interaction between features and handling both categorical and numerical features. You saw regression and classification tasks. They were working no problem. And they are also robust to outliers usually, especially for missing value. They work usually pretty good. On the other hand, what are the limitations? It still can be overfit, so likely to overfit. Although we have pruning techniques, we should properly use it. If you don't use it, it can overfit. They can be sensitive to small changes in data. If you change some of the data, the whole tree structure can change because it's like based on the splitting the data to the left and right. And your data set, if it's changing a lot, that you cannot rely on one tree. That's a little bit kind of weakness point. And they are limited to handling continuous targets somehow, but it's still working. But for continuous target, you can see that in regression, we had a line that whatever the value was in continuous, we could give some prediction over there. But here in the tree, actually we are kind of discretizing. We are kind of creating a leaf that leaf only represents the average of the values that are there. And always, whatever that goes to there, you only get one value. Whatever is in this range, you get like 20. Not 20.5 sometimes, not 20.3 sometimes. It's kind of discretizing in small amounts over there, and that's limitation. But it's still we know that in our prediction models with regression and other, we have lots of error there. For example, when we were plotting the data for like this was the error that we had. And if you compare this error with that error, it's almost the same and not big deal still. But of course, it's kind of limitation. What are the real-world applications that decision trees are popular to be used? Diagnosing the medical decision, diagnosing the diseases is popular to be used, and medical decision making also is popular to use. Customer segmentation, decision trees are popular to be used. Fraud detection, anomaly detection are good applications to use decision tree. Recommender systems and personalized recommendations is also another field that decision trees are popular to use. Credit scoring and risk assessment also are popular to use, but we are not limited to this. You can apply this problem to image processing, image classification task. And it still can work pretty fine based on the features that you have there. But of course, if you have big data set, we prefer to go toward neural network deep learning based on the data size. So now we can answer how decision trees contribute to advanced algorithms. One of the points is ensembled method. In ensembled method, now I'm talking decision tree can be included where? Not only up to previous slide, we saw how it can solve problem. Now we can say, okay, is it advanced technique that we can use decision tree inside? The answer is yes, we can. One of them is ensemble methods. Ensembled learning or ensembled method is popular also in machine learning. What does it mean? It means that if you want to solve the problem with ensembled learning, it means that you want to have different techniques, different algorithms that solve one problem. Then you want to compare which one is better, then use the output of which one is best for you. For example, you have a problem that is critical, you apply regression, you apply neural network, you apply deep learning, you apply different techniques that we studied in this class. All of them are able to solve. We saw, we also implemented many of them. Then you get output for each. Then you can say that, okay, which one was the best based on different techniques and choose that one. This can be called ensemble learning. But traditionally, there are some techniques that are called ensemble. What does it mean? It means that instead of saying combination of very big different techniques, we have a technique that already is ensembled itself. And one of them is random forest that today we will see how it's working. For example, random forest. For example, gradient boosting are based on the ensemble method. That today only we will see random forest. If you are interested in, you can have a look how gradient boosting is working also. Decision trees can provide initial splits in hierarchical clustering algorithms too. If you have an algorithm that works in hierarchical form, hierarchical means that in like level. Then you can use also decision tree over there to create initial splits. On the other hand, we can use decision trees for feature selection also. Oh, you may say, okay, that's very complicated now. We already use decision tree for solve problem. Now we say we can use decision tree for feature selection itself. Yes, we can. First, you can run, for example, decision tree for feature selection. After you select the features, then you can run the algorithm that you want. And this is very pretty decent application for decision tree. Any question? If no question, now we will talk about random forest. Okay. So what is the random forest? Random forest is an ensemble learning method, and it's common machine learning algorithm that combines multiple decision trees. So this is very nice. You can think now, combining multiple decision trees. Now it means that instead of having one decision tree, I would like to have different decision trees. And I defined already ensemble learning. Now you should know how it works based on these only two definitions. It is to propose and generate the single output as what we want. And as I mentioned, you have the data set. We want to generate multiple decision trees. That these multiple decision trees, each one of them give you some value as prediction of the class label or continuous as regression. Each one of them will give you something. And you can apply some different techniques. For example, majority voting. If two of the classes say it is 2, the value is 4, for example, one says something else, then you can rely on these two that most of people are saying the same thing. It's like consensus. How many people are saying more, voting for more, then you choose it. Or instead you can say get average of all of them. Whatever the value they say, get average and give it as output. And this technique basically called random forest. But of course there are some points that we need to be aware and consider about especially ensemble of the decision trees. First point is that random forest creates multiple decision trees, and each of trees trained different based on different subset of training data that also the features that we have are randomly chosen. What does it mean? It means that so if I draw, for example, 2, 3 here, we have the data set that from this data set, randomly choosing data are going to your different trees. And this approach is called, I think I have it, bagging, which means that you have randomly you give it to different data sets. We have different ones. What is the purpose? The purpose is that different trees will construct in different forms. And also usually repetitive values or replacement is allowed here too. It means that, so for this data, this specific data, we can use it here and we can use it here too, not only just use one that finished, not splitting, not like cross-validation. We don't split it like false. The replacement is usually allowed. On the other hand, the features, we can say, okay, from this data set, I have 5 features. Maybe I can use 3 of them here randomly, again 3 of them here randomly, 2 of them here randomly, 5 of them here randomly. I have different trees based on, I can have different trees based on different number of features over there randomly, so that my trees are evaluating from different perspectives, each tree, the data, and finally give you some value, that this value you can use it as prediction of what you want exactly to be. So random feature subset, I explained, randomly select subset of features for your random forest trees. So randomness, I have a point here, helps reducing the also overfitting over there. We say, okay, if we want to build trees in random forest, for each tree we use same recursive process to construct it. Exactly the same process that we studied for decision tree for construction. That process is same, we don't change it. Usually in prediction task, what is happening? Final result, as I explained, can be voting the prediction for prediction. In regression task, it can be averaging the prediction value, or you can say, okay, I don't want to average, I want to report, for example, variance or something else. Whatever it is, you can you can report the Gaussian distribution of the data output over there. Based on your task and your need, you can report what you need over there. What are the advantages? Overfitting problem reduced with random forest in comparison to decision tree. It's more robust to outlier and noise because you are using random features and random data over there. Estimation of the features importance at the same time is happening. What does it mean? It means that kind of we are taking different features, and based on that, each tree constructed based on different features. Kind of we are evaluating which features are good or which combination are good, right? The relationship between features also at the same time are studied over there. What are the disadvantages of random tree? Memory and computational cost. Of course, you see we have not only one big tree, we have multiple big trees. So it will be expensive to compute, more memory we need, difficult to interpret. If you have one tree, it's easy to interpret. If you have many, of course, it's harder to interpret. It still can have overfitting problem. We need to still be careful about overfitting. It can happen. And if we run the regression, on the data set that you have against social media. If you run the regression random forest algorithm, you will have something like this. I set the parameters to 5 only, so to generate 5 random decision trees, and the output looks like this for the data. Decision tree for regression 1, regression 2, 3, 4, 5, and you can see that based on the data randomly split it and the features that chosen randomly, we have trees like this. If you want to implement based on library, again it's simple. From scikit ensemble, we import the random forest regression. Then we create the random forest with some features. Number of estimators equal to 5. Number of estimators is same as number of trees that we have. Here we have 5. And random state, I put it 10 here. Random state is like random seeding in Python, that every time you generate random number, next time you run the same code, you expect same output, right? Then this random seeding, make sure that if you run it 100 times in different computers, you will have same randomness. But if you don't want it, you can remove it and it will be random completely every time the trees will be new. And regressor that fit the X features and output Y will generate through the random forest tree length. Usually we have more than 100 trees, but because I was not able to plot it, I set it to 5. So if I want to summarize today's course, we answered what is the decision tree first. Then we introduced different splitting measures of the decision tree, for example, Gini, for example, mean square error for regression. We discussed how to find threshold for best feature. For threshold best feature, we said that we can have heuristic or greedy techniques that can apply very quick search on the decision tree problem. And anything that you can apply for yourself, you can just write a search, bubble search, or different kinds of search to minimize the threshold value, the objective over there. We discussed advantage and disadvantages of the decision tree algorithm. Then we saw the example based on the dataset that you have. Then we understood finally random forest by using different decision trees. So of course you will have also practice after I explain the implementation code for you, what you're supposed to do after I explain the code. You need to continue give an example, compare decision tree and random forest to see which one is working better. But of course, if you want to compare two algorithms, if you have classification, we had many metrics there. For example, precision, recall, etc. If you want to consider the regression task, we have, like, for example, starting from mean square error and different metrics over there up to cross-validation. If you want to consider two different models, random forest is a model, decision tree is a model, if you want to compare it, you should implement metrics so that based on example that I will give you, you need to compare to see for one of the data sets that you like or data sets that I gave you already, which one is working better? Decision tree works better or random forest works better? How you can do that? You first construct the model, then you need to apply, for example, cross-validation, sample the data and give to both models to see what's the output, calculate the error, then you compare the error. And then you can say, okay, which one of the models working better for this data set? Clear? Any question? Okay, good. So let me, before you forget the details, the implementation is simple. I quickly show the implementation, then you can have a small break, then come to do practice.